Hello and welcome to lecture number 9 of the course Robot Motion Planning. In the last class we looked at C-space mainly for mobile robots. Today we'll look at C-space for serial arms, and then we'll move on to how to do path planning for serial arms in C-space, and also we'll look at the topology of C-space. Okay, so we continue from where we left in the last class and briefly revise and then move on. So in the last class we were looking at C-space for mobile robots, and we saw that the obstacles get enlarged by the amount of by the radius of the mobile robot, or if it is a triangular robot, then we look at the angle by which it is rotated and correspondingly increase the obstacle to form the C obstacle. Then we moved on to the C space for serial arms. Today we start off from there. Let me define the problem before we move on. So we have a two-link manipulator here. Okay, so this is one link and there is another link. And basically there is an obstacle here. So this is my base and there is an obstacle here. Let me say that there is an obstacle here. Now I want to go from some initial point. Let's say I have an initial point here and this is my goal point. I want to go from the initial point to the goal point. Okay. The objective is to find what are the various paths by which I can go from the initial to the goal point. And if a path exists, how many paths exist, or if no path exists, then we also have the algorithm should also be able to say that no path exists. Okay. Now this is basically Cartesian space. Why is it Cartesian space? Because this is my x-axis, that's my y-axis. Okay, so this is my xy axis. Now path planning is to be done in C space. So now what we can do is we want to convert this into my C space. How do I do that? Basically we look at, I start off by saying that we have two variables here, theta 1 and theta 2. So I have theta 1 and theta 2. So we start off by saying theta 1 is equal to 0 degrees. That means my arm is completely stretched in the forward direction. Okay, that means if this is my arm, I'm just drawing a link diagram. This is my theta equal to 0, and this is theta 1 equal to 0, and this is theta 2 equal to 0. I start from there. Okay. Then what I do is I start with theta 1 equal to 0 degrees, and I move theta 2 from 0 degrees to 360 degrees. Okay, that means I take one circle here like this. Okay. Then I increment theta 1 by 1 degree. Okay, so my theta 1 comes here now. Okay. And then I do the same thing for theta 2. I go from 0 to 360 degrees. What would happen is I get another circle. Okay, so I keep doing this, and what we do get is, so if I do that, what I will get is, if this is a two-link manipulator, I'll be getting this set of circles which are moving like this. Okay, so I'll be getting this set of circles which are moving like this. And this is this is basically my theta 1, which is going round like that. So this is my theta 1, and for every starting from 0 0, this is my theta 2, then next is my theta 2 again. So this is theta 2. So what we are seeing is that the shape of the C space that we are getting, if you can imagine, this is what we call a torus. Okay, so this is a torus shape. Now the torus is something like the tube of a bicycle. Okay, you must have seen a bicycle tube. So when you inflate it, it forms a torus. Okay, bicycle tube, then a motorcycle tube, they're all torus. So this is my theta 1, this is my theta 2. Okay, now this is different from Cartesian space. In Cartesian space, basically we are talking about x and y. So this is my Cartesian space. This is x and that is y. Okay, so you can see that this space and this space are different now. This is my C space. Now, if there is an obstacle there, this obstacle here, then the obstacle will also appear somewhere here, okay, on the C space itself. That means on the torus. Okay. So when I'm doing my path planning, say I want to go from this point to this point, this is my goal point, then essentially it is similar to saying that I can find from inverse kinematics, I can find what is theta 1, theta 2 corresponding to that point, right? And I can find the theta 1 dash, theta 2 dash corresponding to this point. So it will be some theta 1, theta 2 which will come here and here, just for example. Okay, suppose this is my theta 1, theta 2 dash, and this is my theta 1 dash, theta 2 dash. So when I'm finding a path, I have to find a path which is going to go like this. Okay, and if there's an obstacle, it cannot go from here. So the path planning is being done on the surface of a torus. Okay, and the C space of this serial arm is a torus. So the object is going to become like this now. Okay, so in the earlier case, it was very easy to say what was the shape of the object in the case of the mobile robot, because the C space and the Cartesian space, they looked alike, although they were different spaces. Okay, but here it's completely different. Okay, so let's look at this. How do we generate the C-space? Basically, I'm taking this two-link manipulator, L1, L2. Okay, the link lengths, theta 1, theta 2 are the... So what I do is I get my coordinates 0, 0 here, and I get my coordinate x1, y1 at this point, and x2, y2 at that point. Okay. So what I'm basically going to do is, as I just explained, I'm going to vary theta 1 from 0 degrees to 360 degrees in units of 1 degree each, and then I'm going to vary theta 2 from 0 to 360 for that corresponding theta 1. Okay, and I'll get the coordinates of these points, x1, y1, x2, y2. How do I get that? From my forward kinematics equations, I know that x1 is equal to L1 cos 1, and y1 is equal to L1 sin 1, and x2 is equal to L1 cos 1 plus L2 cos 1, 2. y2 is equal to L1 sin 1 plus L2 sin 1, 2. Okay. So I've got these points, the coordinates of the points. The origin is 0, 0. So if I connect 0, 0, 0, 0 with x1, y1, this is actually my link 1, right? And if I connect x1, y1 with x2, y2, this is my link 2, right? Now, if there is an obstacle there, let's say I have an obstacle here, like this, there's an obstacle. So if I want to find intersection with an obstacle, I want to find the link hitting an obstacle. Hitting an obstacle. This basically means intersection between a line and a circle. All right. So this is basically an intersection between a line and a circle. So basically, what we are seeing is that for different values of theta 1 and theta 2, as we are covering the full space, theta 1 starting from 0 to 360 degrees, okay, in increments of 1 degree. And for each theta 1, we are varying theta 2 to 0 to 360 degrees, okay. And by putting these values in this equation, we can get x1, y1, x2, y2, connect this by straight lines, get the links, see if they're intersecting with that obstacle. If they're intersecting with the obstacle, we know that the links are hitting the obstacle. Okay, I'll come to the program in a little bit more detail a little bit later. But this is basically how we find out how we go from the Cartesian space to the configuration space for a serial arm. Okay, now this is something like this, that as I just explained, that theta 1 is at this point 0, 0, okay, and theta 2 will be a circle. So let me go here again. So for this 0, 0, this is my theta 2. Okay, now theta 2 rotates for every theta 1, and what we get is a torus. Okay, that's how we get the shape of a torus. Okay, now if you're talking about a torus, and we just said that the path planning has to be done on the surface of this torus, then it is not easy to visualize. Okay, so path is not easy to visualize here, okay, unlike in the case of a mobile robot. So what we do is that we basically take the torus, and in order to be able to visualize it, let me draw the torus here. Okay, so this is my torus. Okay, so what we do is basically we cut the torus. So if you can visualize this, what we do is I will cut the torus here. So if I cut it, if you cut a bicycle tube, what will happen? This will become a cylinder like this. A little exaggerated, but I hope you understand. Okay, so I cut it here and I stretch it out like this, if you can imagine. Okay, so it becomes a cylinder. Then what I do in this cylindrical pipe, what I do is I cut it here again and I open it like this. So if I open it, what will happen is this will become like this. Okay, now this is my theta 1 and this is my theta 2. Okay, so from this shape I have come to this shape. Again, this is my C space. It is not Cartesian space, but it looks like Cartesian space. Here it is easier to visualize. Say for example, now if you have the obstacle, and the obstacle is something like this. Okay, so it has some funny shape. Okay, like this. This is my obstacle. Then I can do path planning. I want to go from here to here. I can do path planning like this, because the robot has become a point, and this in my configuration space, this is becoming my obstacle now. So this is obstacle space and this is free space. Okay, so what we do is we form the torus. We write a program to form the torus, and we cut it open and display it like this. and then do the path planning, because it is much more easier to see and understand. So something like this. So you have a flat mat. If you rotate it, you get a cylinder. Okay, if you roll it up, and then if you roll it again about this axis, what you get is a torus. So the reverse is, if you cut it and open it, what will happen? It will be a cylinder, and then if you open it, it will be a mat. So it's like folding a mat and then again folding it in the other direction. So this is a torus, right? So this is what I was meaning by saying that you cut the torus, open it up, it becomes a cylinder. You cut along the axis of the cylinder, okay, and what would happen is, and then open it up, what you get is a rectangle, okay, which is similar to the Cartesian space. It is not Cartesian space, but it looks like Cartesian space. Okay, now this is something we talked about. So the shape of configuration space for mobile robots and serial arms is different. Okay, now in the case of serial arm, it is a torus, and what we do is we cut the torus in two locations. So this is my, if you're starting from here 0 0, this for example, then this is my theta 1 and that is my theta 2. Okay, so for every theta 1 theta, there will be a theta 2, so there will be a circle. So all of it connected together becomes a torus now. And in order to visualize it, what we do is we cut it open. So this is my two-link manipulator, something like this. There's an obstacle. Okay, so there's an obstacle there. So the obstacle will come on this surface now. It will have some shape. And if I want to do path planning from one point to another point, I have to do it on this surface now. So I will cut it, open it, make it into a rectangle, and then do path planning on that. So this will be something like this, my obstacle space. Okay, so as we go along, it will become more and more clearer how this is done. Okay, so how to generate the C space and obstacle space in the form okay, so basically what we do is we write a program. So this is basically a program. Okay, you can write in MATLAB, you can write in C language or C++ or whichever language you want, or Python. So basically what it is doing, what is the logic here, is that we have this two-link manipulator which has two links, L1, L2. This is the point 0 0, this is x1, y1, this is x2, y2. Okay, that's my theta 1, that's my theta 2. That means, and suppose there is an obstacle. Okay, so there is an obstacle here. So basically what we are doing is, basically we are running two for loops. Okay, so I have one for loop here which is taking from theta 1 is going from 0 degrees to 360 degrees in intervals of 1 degree. And I have one more for loop which is taking theta 2 is going from 0 degrees to 360 degrees, okay, at intervals of 1 degree. Okay, so there are two for loops, and I compute x1, y1 from that equation. Then I compute x2, y2. I just explained how to get that values. Okay, then I plot straight lines. Okay, so there is the plot command in MATLAB, for example. So you connect 0 0 with x1, y1. So there is one, and then you can plot straight line again. You connect x1, y1 with x2, y2. Okay, so we are connecting this by straight lines. Now this is basically what is my links. Now you need to check for intersection. Check for intersection with circle. Now you know that you know the equation of the circle, and you also know that how to check for intersection if any part of this line is inside that circle, or if the line is touching the circle. That we can check from geometry, right? The other way is if the link is a rigid link. For example, we say this is a rigid link like this. That means it has some geometrical shape. That's also okay. So what we can do is we can check for interference between the rigid geometrical rectangle and the circle. So in MATLAB is very easy. It can do the intersection very easily. Okay. So what we do is we run these two loops. Okay. And for every value of theta 1 and theta 2, we check if there is intersection. Now, if there is intersection between the circle, what we do, we put a particular color. Say, for example, this is blue color. Light blue color is the obstacle. So this is my theta 1 is going in this direction, theta 2 is going in that direction. Okay. So for theta 1 starting from 0, okay, say in this particular case, for example, if it is like that, okay, this is just giving you an example. We start from theta 1 equal to 0, theta 2 equal to 0. Now at theta 1 equal to 0, as the link theta 2 is rotating, after this angle it will hit that object. You can see intersection will be there. So from here to here there is intersection, right? So what would happen is I'm going to mark it with this particular color, same color as the obstacle, and I proceed like that. So okay, so wherever there is intersection, I will mark with color of the object. Okay. So what will happen is you will end up getting a figure like this. Now let's look at this very carefully and understand. On the right side is my Cartesian space. This is my Cartesian space, this is my C space or C obstacle space. So we have a link, so 0, 0 is here, that's one, the 0, 0 in the Cartesian space. Then we have a link which is 3 here, okay, so this is coming till 3, okay, the link length is 3, and there is another one which has the link length of about 2, okay, so this is the other link length, okay. Now what we are doing is we will start from theta 1 equal to 0, 360 intervals of 1 unit, and theta 2 goes from 0 to 360, okay, intervals of 1 unit. So when theta 1 is 0, you can see theta 2 is going to rotate, this is my theta 2, is going to rotate like this, like so. From here to here, this much range, it is hitting the red obstacle, okay. So theta 1 equal to 0 is here, look at the left side figure, okay. Theta 1 equal to 0 is here, so at 200 degrees, so we are measuring counterclockwise, so it is going like this till here, about 210 degrees it is hitting. So I'm marking it with orange color. Why? Because this is marking it with pink color, because this obstacle is pink color, just to know which obstacle it has hit, because there are 3 obstacles here, okay. So there is a yellow obstacle, a blue obstacle, and a pink obstacle. So theta 1 equal to 0, it is hitting in this region which I'm marking here. Then I increment by 1 degree, okay. So what happens, it goes to the next one. So this is incremented a little bit. Again we take one round, and when it takes one round, link 2 is going to hit this again. So till here to here it is hitting again, okay. So wherever it is hitting, I put a mark with that respective color. Then I move further, and we see that somewhere around here, equal to 25, so it's about there, the link 2 will start hitting the yellow obstacle now, okay. It hits the orange, it was hitting the pink one, but now it will start hitting the yellow one, okay. So it is somewhere here, okay. So we increase theta 1 equal to say 25 degrees, for example, and we rotate theta 2 completely. So we see that it starts hitting. Now it is hitting the yellow obstacle, so I put a yellow color. So I do that until I go completely theta 1 0 to 360 and theta 2 0 to 360. That means I've covered the full space. And what I do get is theta 1 is on this axis, theta 2 is on that axis, and this is my C space. Now, is there any correlation between the shape of the object in Cartesian space and the shape of the object in C space? It's very difficult to say. Now you can also guess, okay, why we had put colors, because otherwise it will become difficult to figure out which obstacle was which one, okay, because the shapes have completely changed, right? So what we are seeing here is that this obstacle is this one, okay, this is this, and the yellow one is there, okay. And the very funny is that part of the pink one is here also, okay. Now if you can imagine, what actually happened is that it actually formed a torus, and then we cut the torus and opened it up. That's how we are getting the C space like this, okay. So if I were to join it now, okay, if you can imagine, let us go here and imagine this. Suppose I roll it about this is my axis, I roll it like this, you'll get a cylinder, and then I roll it like this again, okay, you'll get a torus, okay. So please, if you're imagining why it is cut here, it is not cut, it's actually continuous. So when I roll it in this direction, this part will get joined with this part, okay. The blue one, this part will get joined with that one, and the yellow one, the yellow part, this part will get joined with this part. So it's actually not cut, it is continuous, okay. And then when I turn it, when I rotate about the central axis, now let me rotate about the central axis, about this axis, and close it, what will happen is this part will get joined to that part. Why? Because this is a continuous object, right? It's not a broken object. So it can't be that one part is here, another part is there, and they're not connected. They are connected, okay? Because we have cut the torus, it has come out like this, okay? So if you just go back a little bit and try and figure this out. So this is what we showed. Okay, so the torus, we cut it here and cut it along that axis. Okay, it is almost like saying you have a flat sheet, you roll it like this. Okay, you roll it and then roll it again about the other axis. So what will happen? It will become a torus. So when we cut the torus, what will happen is we are going to get this kind of a C-space. Okay. Now program generating C-space with different obstacles. Basically what we do, we find the coordinates of 0, 0. 0, 0 is known, x1, y1, x2, y2. Okay. Use two for loops. Theta 1 is equal to 0 to 360 degrees. Okay. And theta 2 is equal to 0 to 360 degrees, intervals of 1 degree. Okay. And find the intersection between obstacle and link. Okay. If there is intersection, put or mark using a color, using the obstacle color. Okay. So this will indicate that we are putting the obstacle color. So what we'll end up getting is a torus, and we cut and open the torus, and what we get is, say for example, a shape like this and a shape like this. Just for example, this may be one obstacle, then we could have another obstacle which is having some other shape like this, like this. Now the colors will indicate which obstacle it was, so that you are also clear as to which obstacle went there, where. Because geometrically it's difficult to correlate and say that, okay, this is exactly what happened, or this obstacle is here. Okay, so this is how we write a program in MATLAB to find out or to convert from the Cartesian space to the C space. So if you have obstacle, there could be an obstacle here. Okay, any obstacle in fact. Okay, normally we put different colors and then code it in color. Okay, so now let's look at the program. We have looked at a program. Now let's look at another example of how the program works. So remember that in this particular case, as shown here, there are three obstacles. Okay, so you can see there is a blue color circle, and there is a green triangle and a red square, and we have a manipulator which is starting from here to here. Okay, that is my manipulator. This is my 0, 0. So link lengths L1 is equal to L2 is equal to 3 units. Okay. Now how does the program start? It starts by saying that theta 1 is equal to 0 and theta 2 is going from 0 to 360 degrees. Okay. And it plots x1, y1, x2, y2 and checks for intersection between any of the obstacles. Okay, so we start here on the right hand side. So this is my Cartesian space. This is my C space. Okay, so we start at 0, 0 here. Okay, in my for loop, and then wherever it is not hitting, it is yellow color. Okay, so yellow color not hitting the obstacle. Okay, so you can see that it is not hitting, only this. You can very well see this. Okay, so when it is rotating like this, only at this angle it will hit. Till here it will hit the second link for theta 1 equal to 0. Okay, so correspondingly it is hitting from here to here, and wherever it is hitting, I am putting a green color. Okay, so wherever it is hitting, the links are hitting the obstacle, I put a green color. If it is hitting the green obstacle, so you can see there is green here. Okay, so I can put any mark, I can put square, I can put rectangle, or I can put circle. In this case, I'm putting a circle. Okay, now let us see how the program works. It will become clearer. Okay, so how this program works is, so this program is written in MATLAB. You can write in any language you want. So let's start slowly and see how this is working. Okay. So the first one is, we have 0, 0 is here at this point, and this is the second link, and the second link is rotated one full circle. So what we have got is a circle now. Now wherever it is hitting there, right? So for theta equal to, I think it is a little bit more, it's over 5 degrees. It starts from 0, 1, 2, 3, 4 like that. Okay, so it is hitting here, so we color it by green. Okay, so this is how the program works, and this is how we are going from Cartesian space. So this is my Cartesian space, and this is my C space. Okay, Now let's see a little bit more how this is going. Let's increase that theta 1. It has gone a little bit more. You can see how it is moving. Theta 1 is increasing and theta 2 is always taking a circle. And wherever it is hitting, look at the shape of the green object. So it has been hitting and then now it is not hitting. Okay, so in this region you can see that it is not hitting. Okay, then we are going forward. So theta 1 is increasing, then it will start hitting the red one. Now it started hitting the red one. So immediately you can see that here it has started hitting the red one now. So theta 2, either of the links can hit or both can hit. Okay, now as we are going further, you can see that theta 1 is increasing more and more. Theta 1 has become 90. It has become more than 90. So theta 1 is somewhere here now. Theta 1 is about 90, more than 90 degrees there now, and theta 2 is taking this circle. So it is hitting the red obstacle and we are marking it with red color on my C space. Okay, we further progress. You can see that it is hitting the red one. It is going further. Now it is hitting the red one. Both the links are hitting the red one. Okay, so you can see that the red color has extended right till the top. Okay, that means theta 2, completely theta 2 is hitting. Okay, it has almost gone like inside the object. You can see that. Here, this is my theta 1. So theta 2 is almost gone inside the object. And that is why right from 0 to 360 degrees. So this end is 360 degrees. Completely it is hitting. It is completely hitting. Okay. So from 0 degrees to 360 it is hitting that. Now we are going further. What is happening is we are start hitting the blue object. Okay, till here it is not touching the blue object. Now we progress a little bit more. Now it starts hitting the blue object. Okay, you can see that. Now on my C space diagram, it is hitting the blue one and the red one. So in this location, okay, at this location of theta 1, it is hitting the blue one as well as the red one. So both are being marked. Okay. Now we move a little bit further. It is going completely up to about 270. Then it comes to 360 and it is complete. Okay. Now if you try and connect the shape of the obstacle and the shape in C space of the obstacle in C obstacle space, what is going to happen is there is very little correlation. It's difficult to say which one is which one. Okay, which was the circle, which is the rectangle, and that is the reason we coded by color. So it is very easy to know that okay, this is the rectangle, this is the triangle. Okay, now in terms of continuity, I can rotate, I can roll this sheet up. If I roll it, what will happen is this will get rolled like that. I hope you can imagine that. So this side will get joined with that side. This side will get joined with that side, and this will get joined with that. Okay, so it is actually continuous, it's not broken. Then if I rotate the sheet rotate the cylinder about this axis now, okay, what will happen is this will close. So now what will happen is it will become a torus. Okay, so on the surface of the torus, if you can imagine, this is going to be the obstacles now. This is my obstacle, C obstacle. Okay, and this is my free space. So this is my free space and this is my obstacle space now. Okay, they are connected. So this side is connected to this side. Okay, and this side is connected to this side. Okay, because it is a torus actually. So you can write this program and try and draw it and figure out how it works. So this is showing it very quickly how we got this complete shape. But now you'll remember something. Okay, that we talked only about 2 degrees of freedom. Okay, we only talked about 2 degrees of freedom, and we have theta 1 and theta 2 because it was a 2 degree of freedom system. Okay, so it was easy to visualize. So when we converted, this is my theta 1 and this is my theta 2 because the serial arm actually had 2 degrees of freedom only. Okay, this theta 1, theta 2, and that's why we could convert and draw it easily like this. Now suppose you are going for a higher degree of freedom system. Suppose I have a serial arm, for example, which has 6 degrees of freedom. So I have a 6 DOF arm. That means there are 6 thetas. Okay, and now if you have 6 thetas, then you have to draw the 6 thetas. Okay, how are you going to draw? How are you going to visualize? Now there is a problem. Why? Because we are living in 3D Euclidean space. Okay, and it is 3D, so we have at most 3 dimensions, which is my x, y, z. So if I have more than those dimensions, I find it difficult to draw. Okay, how do you draw? We don't have the degree of freedom in Euclidean space. For example, this humanoid robot or biped robot character, this can have like 36 degrees of freedom. This means there are 36 thetas. and each of this theta is an axis. How are you going to draw it? Okay, and how are you going to represent obstacles? How are you going to do the planning? Say, for example, this one is showing Q1 to Qn, where n is a large number. So this is actually planning in higher dimensional space, which is very difficult to visualize also. 2 degree of freedom, we are lucky that 2 degree of freedom was very easy. We could visualize it very easily, and that is the reason we can explain very clearly that, okay, this is how it looks like. What about higher dimensions? Higher dimension, there is a problem, okay, because you cannot draw it in Euclidean space, and it will be very difficult to visualize where it is going. So that brings us to the next topic, that if you realize what we are doing here is we are basically doing the motion planning in our C space, okay, not in Cartesian space, okay. So this is my Cartesian space. Here we are Cartesian. This is my C space. This is C space. So we are doing the motion planning in C space because the robot is a point now, okay, and everywhere here is free space, okay. So suppose I say I want to go from here. This is my initial point. I want to go to goal point, okay. So I can find a path like this because it's a point which is moving. As long as it doesn't hit the obstacle, it's okay. That's a path. Now once you find the path, you have to go. So from here we came here, Cartesian space to C space. Now from C space we are finding the path, and we are going back to the real world because the robot is moving in the real world, isn't it? So basically it means that we are moving in between spaces now, Cartesian space to C space, and C space back to Cartesian space, okay. So this is some kind of mapping which is going on, and that is where topology comes into picture, that we have to look at the topology of spaces, okay. So topology is a branch of mathematics that considers properties of objects that do not change when subjected to arbitrary continuous deformations such as stretching or bending. For example, if you have a rubber sheet, let's take this example, you have a rubber sheet, okay, and I draw a circle in there, okay. Suppose I stretch it, what is going to happen? The circle is going to become like this, probably an ellipse, okay. But the properties of the object do not change when subjected to continuous deformations. What property of this object? First of all, it is a closed curve, so that property will remain a closed curve. So a circle can become an ellipse, but it's still a closed curve, okay. It cannot become a straight line, for example, okay. Points which are inside the circle will remain inside the circle, they cannot come outside, okay. So the properties remain irrespective of the deformations that they are subjected to, okay. And this is basically what we study in topology. So a topological space is a set endowed with a structure called topology, which allows defining continuous deformations of spaces and more generally all kinds of continuity, okay. So a topological space is a set endowed with a structure, and this is basically called the topology of the space. So the motivation behind topology is that some geometrical properties or problems, like path planning is one of them, okay, depend not on the exact shape of the objects involved, but rather on the way they are put together. Example, the square and the circle have the same properties in common. For example, if I take this rubber sheet again, okay, and I draw a square, and I subject it to deformations, I pull the rubber sheet, okay, what will happen is a square is a closed curve, so it will remain a closed curve. Points which are inside will remain inside, they cannot come outside, okay. So in a sense, a square and a circle are the same as far as topology is considered, okay, they are same, okay, they are topologically similar, okay. Now this is useful in our case of path planning. We'll see as we go along how. Now what are the different spaces? We are talking about the topology of space, right? Now Euclidean space is XYZ, three-dimensional Euclidean space we are familiar with. We also call it Cartesian space. C space is theta 1, theta 2 for the 2 degree of freedom arm we talked about. Now the path is planned in C space, right? So I have a link like this, 2 degree of freedom link, and I drew the equivalent with an obstacle maybe. So there is an obstacle here, so there is an obstacle here. So I drew the corresponding obstacle space here. This is my obstacle, this is my theta 1, this is my theta 2. Now I want to find a path from one point to another point, from this point to this point. I found a path. So from Cartesian space, I went to C space. I found the path. Why? The robot has become a point. Okay, so this has become a point now. And this is my free space. This is my obstacle space. So I found a path now. Now, after having found the path in Cartesian space, I have to move back to the real world. Okay, so that means I'm going in one direction and then I'm coming back again. So if this is my forward transform, this is my inverse transform between the spaces. Okay, so basically I'm going with one transform in the forward direction and finding the path and then coming backwards. Now, if the inverse doesn't exist, then again it's of no use because the path cannot be executed in the real world. Right? So this is what makes it that if there is no relation between these spaces, then the path cannot be executed by the robot. You can go in the forward direction, you can't come in the backward direction. Okay? So these are things which are studied in topology of configuration space. Okay? Now, topology is the intrinsic character of a space. This is something we have seen, that topologically a circle and a square are the same. Okay? Because both of them have the same properties. They are closed curves. Points which are inside the curve cannot come outside when subjected to deformations. Now, two spaces have different topology if cutting and pasting is required to make them same. Okay. Now, if you have to cut, if you want to take out the here, suppose I have a circle and I have points inside. If I want to take these points outside, I have to cut actually. Okay, then they can come out. So, two spaces are different topologically, or they have different topology if cutting and pasting is required to make them same. Okay. Now, a path plan or an algorithm for one type of space is made, then it can be carried over to another space if they are topologically equivalent. Otherwise, they cannot be transferred between spaces. Okay. Now, where did this study come about from? Basically, it was started off by Euler, and he demonstrated that it was impossible to find a route or a path through the town of Kinsberg that would cross each of the 7 bridges exactly once. So this is my town of Kinsberg. Okay. Now if you want to go from this side to that side, there are 7 bridges. So this is 1, 2, 3, 4, 5, 6, 7 bridges. Now he said that it is impossible to find a path to the town of Kinsberg that would cross each of the 7 bridges exactly once. So the catch is exactly once. So you cannot go from one side to the other side by crossing each of the 7 bridges exactly once. Either you cross less number of times or you cross more than once. Okay. Now there are these green bridges you can see. There are 7 bridges. Okay. Now this problem has nothing to do with the dimensions of the bridges. Okay, this is something that you should note very, very clearly, that there are 7 bridges here, and this problem has nothing to do with the dimension of the bridges. So the bridge is small or big, it doesn't matter. And this is essentially what topology is talking about, that this has nothing to do with the dimension of the bridges. Okay, it essentially has to do with the topology of the space we are talking about. So if you want to go from one side to the other side, for example, you go like this, start from here, go like this, like this, like this, like this, and go to the other side. Okay. You have crossed only 1, 2, 3, 4 bridges. But you can't cross all the 7 bridges at least once and go from one side to another side. And this has nothing to do with the dimension of the bridges. Okay, this is something that is important here. That this is where the study of topology of spaces came up. Now, if you look at in terms of topology, the cow and the sphere, they are the same space. Okay, because simply by deforming, we can go from one space to another simply by stretching or deforming. We are going from one to the other. Okay. Now, any object with any point which is on the surface of the cow is still on the surface of the sphere. It can't go inside the sphere. Similarly, any point which is inside the sphere cannot come outside the sphere. Similarly, that for the cow, any point which is inside the cow cannot come outside. So topologically, this is the same. They are the same topological space. Something like the circle and the square we talked about. Now, there are many examples, the donut and the mug. So, this is a donut, something like a torus, and this mug. Okay, they are topologically the same space. okay, because simply by deforming we are going from one space to the other space, okay, and hence they are topologically the same. So it is very easy to figure out that any point which is inside the donut will remain inside the donut. Any point which is on the surface of the donut will remain on the surface of the cup also. Okay, it cannot go inside. Okay, so this is something that is interesting in terms of topology. There is also an interesting theorem called the hairy ball theorem of algebraic topology, which says that one cannot comb the hair flat on a hairy ball without creating a cowlick. Now you know that when you're combing your hair, what happens is you're trying to make it flat. This is a flat surface, but your head is spherical. So you're trying to make this flat surface sit on a sphere. Okay, so you can do that only locally, but you cannot do it globally. We'll come to local and global as we go along. Now, if you try to do that, what would happen is you'll end up with a space like this, which is called a cowlick, either one or two of them. Okay, so this is supposed to be the hairy ball of algebraic topology. Now, we have to look more further into this in terms of the mapping actually. Okay, so let us say we have two spaces. We have S and we have T. These are two spaces. We can talk about them as Cartesian space and C space. Okay. Now there is a mapping phi which is taking elements from C. These are different elements of C to elements of T. Okay, maybe this is my mapping which is phi. Okay, so this mapping phi places elements of S into correspondence with elements of T. Okay, S and T are two different sets. Now if all elements of T are covered by the mapping, then it is called a subjective mapping or onto mapping. Now if each element of T has correspondence with at most one element of S, then phi is injective, okay, or 1:1 mapping. Okay. Now if phi is subjective and injective, then it is bijective, which case an inverse exists. So we talked about going from one space to another space and then coming back. Okay, that if you find the path in configuration space, you need to come back to the Cartesian space, otherwise it's of no use, which means the inverse has to exist, and the inverse will exist if this phi mapping is bijective. That means it is surjective. That means all the elements are covered and there is a 1:1 correspondence. Okay, so please note the importance of this bijective mapping. The other point is phi is smooth if derivatives of all orders exist. We said that we have a path from initial point to goal point. Okay, that's my point. Now this path has to be continuous. So continuous means it is smooth if derivatives of all orders exist. Okay, so it has to be bijective and it should be smooth. So phi S to T is a bijection and both are continuous, then phi is a homomorphism. But one step ahead of that, a smooth map U to V is diffeomorphic if phi is bijective and phi inverse is smooth. Okay, this is even more important. Then U and V are diffeomorphic. Okay, so we are looking at two terms, what is homeomorphism and diffeomorphism, and it basically has to do with bijective mapping and which is smooth. So if it is bijective, inverse exists. If it is smooth, it is continuous. Okay, and both of these are important when we are going from one space to another space. Now, why is mapping important? Now, it's very easy to understand why mapping is important, because in the case of the serial arm, I'll just give an example of the mobile robot also. So we have a mobile robot which is here, and we have there is a steering wheel. Let's say there is a steering wheel here. So these are my steering wheels. Okay, this is my steering wheel at a particular angle. Okay, and this is my local axis, x dashed, y dashed. Okay, and this is my xy. Okay. Now there is an obstacle here. Let's say I want to avoid this obstacle. Okay, so basically what we are doing is we are going from here to my to the C space, which is my C space here, and we have a particular shape, and then we are finding a path from the initial point to the goal point. Maybe this is my goal. Okay, so I find a path which is taking me from the initial point to the goal point like this. Now once we have found the path in the C space, we have to come back to the real world now. That means at every point here, I have to find out what are the velocities which will actually take me there from doing inverse kinematics. So this is the forward map and this is the inverse map. Okay, and both have to exist. And the path has to be continuous. We'll see why. Okay. So this is the importance of what we call a diffeomorphism, which is bijective, and phi inverse is smooth. Okay, when we are mapping between two spaces. Now you can also appreciate that if this phi does not exist, phi inverse doesn't exist, then there is actually no point. Okay, because the path cannot be transferred to the real world. That is one. The second is, if the spaces are same for this mobile robot, if the spaces are same in which it is moving, in which we are talking about the path, then we can transfer the path between different spaces also, provided this mapping exists. Okay. So now, for example, cases where the mapping may not exist, the inverse may not exist, or it need not be continuous, is, for example, you have a circle. So we can call this FC. So it's a circle, for example. Okay, the ends have to meet. So this is a circle, and this is an ellipse. So this is an ellipse. Okay. Now in the ellipse, let's call it FE, and we have a racetrack. Racetrack is two straight lines joined by two semicircular points. Okay. Now FC is diffeomorphic to FE. FC is diffeomorphic to this one. Okay, but neither of them are diffeomorphic to FR, the racetrack, which is FR. Why? Because FR is not continuously differentiable, while FC and FE are. That means at these points, they are not continuously differentiable, where the semicircle is meeting the straight line. Okay, so, and hence it is not diffeomorphic. So FC and FE are not diffeomorphic to FC, because FC is, sorry, FR, because FR is not continuously differentiable. So we need to look at this one and smooth. So for smooth, it has to be continuously differentiable. Okay, because you need the velocities. Okay. Now, mapping between Euclidean space and C space, all the C spaces seen so far could uniquely be specified by n parameters, where n is the dimension of the C space. Okay. For the planar mobile robot, n is equal to 3, n is the dimension of the configuration space, while for 2 degree of freedom arm, n is equal to 2. That we have seen. Right. Now, the reason we are able to do this is that these C spaces are locally like n-dimensional Euclidean spaces. Now, in this case, we are able to map. Why are we able to map? Because we are able to map because the C spaces are locally like n-dimensional Euclidean spaces. That is the reason why we are able to map. Okay. Now, to be able to map, to go to the Cartesian space, from Cartesian space to C space, and then to come back to the Cartesian space again, we need to have a mapping which has the inverse, and that also has that is also smooth. Right. Now let's see a little bit further into this mapping business. So next we have looked at these terms. These are some terms that you need to understand very clearly. One is this question of topological space. We just talked about topological space, the properties, that is bijection and being smooth. Now we have another term which is called a manifold. Okay. So a manifold is a topological space that locally resembles Euclidean space near each point. So a manifold is a topological space which locally resembles Euclidean space near each point. Okay, it is locally, not globally. Okay, what is this local and global? Is that all throughout it may not represent, but at local points it does represent Euclidean space. For example, Cartesian space and a C space. Okay, and configuration space. So this configuration space, Cartesian space is a Euclidean space, right? 3D Euclidean space. Now C space resembles Cartesian space locally. Okay, and that is one of the reasons we were able to do this mapping, because locally it does represent, and configuration space is a manifold. Okay. So manifold is a topological space, for example, in our case it is C space, okay, that locally resembles Euclidean space near each point. The structure of configuration space is a manifold that resembles Euclidean space near each point. Okay. So what this basically also means that at each point Q, there is a one-to-one map between a neighborhood of Q and a Euclidean space R raised to n, where n is the dimension of the C space. Okay. Now this is a definition. A set K is a k-dimensional manifold if it is locally homeomorphic to R, meaning that each point in S possesses a neighborhood that is homeomorphic to an open set in R. Okay, this is maybe a little confusing, but as we go along, it will become clear. So it basically means that you can map from C space to Cartesian space, because both these spaces, the configuration space resembles Cartesian space locally. Okay, and configuration space is a manifold. Okay, and that is the reason why it is called a manifold. Now, what is this local resembling space locally? So if you look at this example, it becomes very clear that what we are talking about. So let's look at this case where we have a sphere and we have a flat surface. This is similar to what we are talking about in the case of the combing hair. So when we are combing hair, we saw that we are trying to make the hair sit flatly on a sphere. Here it is the reverse, where we are trying to represent a sphere by means of flat surfaces. Where can you imagine this? Say, for example, this is the Earth, okay, and these are maps. Now you see that maps are flat, right? A map is a flat surface like this, whereas the Earth is a sphere. Okay, so we are trying to represent the sphere by means of a map. Okay, so locally a sphere can be represented as a flat surface, locally, not globally. Okay, so this is an example of saying that this spherical surface, okay, can be represented by a flat surface, but locally only locally in this region. And that is how we have these maps, and you're familiar with maps, right? Now let's talk a little bit more about structure of configuration space, and then we'll move on. So this is what I was talking about. Okay, so when we're talking about maps represent a spherical Earth, but maps are flat. For example, this one you can see is flat. And how is it that we're representing a flat spherical surface on a flat surface? Because locally you can map them. Okay, so this is a manifold in a way. Now let's look a little bit more. So structure of configuration space: a pair U phi such that U is an open set in a k-dimensional space and phi is a diffeomorphism from U to an open set R is called a chart. Okay, now chart is analogous to its use in cartography or maps. Okay, this you would have heard the word maps, you would have heard of atlas. Okay, you might have used this in schools, maps and atlas. Okay. So essentially a pair U phi is the mapping such that U is an open set in a k-dimensional space and phi is a diffeomorphism from U to an open set R is called a chart. Okay, and a set of charts that are C infinity related and whose domains cover the entire configuration space form an atlas. Okay, so an atlas and C space together constitute a differentiable manifold. Okay. Just to know that configuration space is a manifold because locally it is similar to Euclidean space, that you understand. Now, because it is locally, we can make it represent the Cartesian space or Euclidean space. That is why you can represent the Earth in the form of maps. And if you put all these maps together, basically we formed an atlas. Okay, that is basically the definition of a chart. Each one is a chart, and putting them all together, you get an atlas. Now, connectedness is something that we have to be very careful here. So a manifold is path connected or connected if there exists a path between any 2 points in the manifold. What is a manifold? Manifold, just remember, is a configuration space. Why is it a manifold? Because it is locally like Cartesian space, right? That is why it's called a manifold. Now a manifold is path connected or connected if there exists a path between 2 points in the manifold. Okay. Now the presence of obstacles can disconnect the manifold. Now let's look at this example we were talking about some time back. Now we have the 3 obstacles which are shown here. Now this side is connected to this side. That means this part is connected. Okay, and this part is connected, this part is also connected. However, this part is not connected to that part. Okay, they are not connected. Okay, so when we are making the path, the path has to be connected. Of course, it can't be a disconnected path, right? It should be continuous and connected. So you cannot join two parts in a manifold which are not connected, right? So let's look at the case of path planning, for example. Let's look at this example here. Now in this case, this is an example of two-link manipulator again, 2DOF manipulator. Please look at this. There is one link here, another link there. Now I want to go from this point to that point. Okay. Each of the obstacles are shown there. This is my C space. This is my Cartesian space. Okay. So this one is here, this one is there, and this one is here, and the green one is there. Now I have an initial point here, and I have a goal point here. Now this is not connected because they are not connected. You can see that, right? So this part is not connected to that side. So no path exists. So this says that path does not exist because the manifold parts are not connected. Second is, in this case, we have again 2 degrees of freedom manipulator. This is 1 degree of freedom. This is one link, another link. Now in this case, I want to go from this point to this point. This is my C space. Okay. So this is my start point, that's my end point. But in this case, I can go because this is connected. Okay. All of them are in the void space, in free space. Okay. So this is showing that a path exists from start point to the goal point. Now you can understand why we need to do the planning in C space. Because otherwise it will be extremely difficult in this particular case to even visualize, to try to figure out, doing inverse kinematics, whether it can go from one point, from the initial to the goal point. Now let's look at this case. Now in this case, this is my two-link manipulator again. It has to go from this point to this point. Okay. Now in this case, it is from here to there. This is initial point, that's final point or goal point. Now because this side and this side are connected, okay, this part, when we connect it, when I roll it about this axis like this and like this, when I roll it, this will join like, so this side and this side are joined, which means it can go like this, come out from there and go there, okay, because it is path connected. So you can go from here to here because it is path connected because of this wraparound of the torus. Okay. So this is something that we looked at in today's class. We talked about the ways of drawing the Cartesian space. So today's class we talked about how to draw the Cartesian space for a serial arm robot. And after you make the Cartesian space for the serial arm robot, if you have to find a path, it has to be a path connected, which means that in the manifold there should not be breaks due to the obstacle, and the initial point and the final point should be connected in the manifold itself. We also talked about topology of configuration space. We said that configuration space is a manifold because locally it is like Cartesian space. Okay, so we'll stop here today, and in the next class we'll continue with our discussion of how to find paths which are going from one point to another point. So let's stop today. Thank you.